Hello everyone, welcome back to my channel. I am Jyotsna, pursuing my BE Computer Science from Sri Venkateshwara College of Engineering. Today's topic is quantum mechanics. Topics to be covered are wave-particle dualism, de Broglie hypothesis, matter waves and its properties, principle of complementarity, wave function, eigenvalues and eigenfunction. Wave-particle dualism. The phenomena like interference, diffraction and polarization are attributed to the wave properties of radiation. The quantum theory of radiation and experiments like photoelectric effect and Compton effect describe the particle nature of radiation. Thus, radiation behaves like waves and like particles under different suitable circumstances. Hence, radiation exhibits dual nature. De Broglie hypothesis. In the year 1924, French physicist Louis de Broglie extended wave-particle dualism to a hypothesis, stating if radiant energy could behave like waves in some experiments and particles or photons in others, and since nature loves symmetry, then one can expect the particles like protons and electrons to exhibit wave nature under suitable circumstances. This is well known as de Broglie hypothesis. Therefore, some sort of waves can be even associated with moving material particles called matter waves or de Broglie waves, and the wavelength associated with matter waves is called de Broglie wavelength. The wavelength of a photon in terms of its momentum is given by lambda equals to h by p. Hence, by analogy, the de Broglie wavelength of matter waves is given by lambda equals to h by p is equals to h by mv. Here, m is the mass of the moving particle and v is its velocity. Matter waves and its properties. Phase velocity. The velocity with which a wave travels is called phase velocity, Vp, and is also called wave velocity. If a point is marked on the wave representing the phase of particle, then the velocity with which the phase propagates from one point to another is called phase velocity. Vp is equals to omega by k is equals to E by P is equals to C square by V. Here C is the velocity of light in vacuum and V is the velocity of matter wave. It is also evident from the above equation that the phase velocity is not only greater than the particle velocity, it is also greater than the velocity of light. Hence, there is no physical meaning for phase velocity of matter waves. Wave packet and group velocity. Since the velocity of matter waves must be equal to that of particle velocity, and since no physical meaning can be associated with phase velocity, the concept of group velocity is introduced. Matter wave can be considered as a resultant wave due to the superposition of many component waves whose velocity differs slightly. Thus, a wave group or wave packet is formed. The velocity with which the wave group travels is called group velocity, which is same as particle velocity. It is denoted by Vg and is given in the equation Vg equals to d omega by dk. Properties of matter waves. The following are the properties associated with matter waves. Matter waves are associated only with particles in motion. They are not electromagnetic in nature. Group velocity is associated with matter waves. As a result of superposition of large number of component waves with slightly different frequency, matter waves are localized. The phase velocity has no physical meaning for matter waves. The amplitude of matter wave at a given point is associated with the probability density of finding the particle at the point. The wavelength of matter waves is given by lambda is equals to h by mv. Principle of complementarity. Statement. Bohr stated as, in a situation where wave aspect of a system is revealed, its particle aspect is concealed. And in a situation where particle aspect is revealed, its wave aspect is concealed. Revealing both simultaneously is impossible. The wave and particle aspects are complementary. Explanation. We know that the consequence of the uncertainty principle is both the wave and particle nature of the matter cannot be measured simultaneously. In other words, we cannot precisely describe the dual nature of light. In an experiment is designed to measure the particle nature of the matter. During this experiment, errors of measurement of both position and the time coordinates must be zero, and hence the momentum, energy and the wave nature of the matter are completely unknown. Similarly, if an experiment is designed for measuring the wave nature of the particle, then the errors in the measurement of energy and the momentum will be zero, whereas the position and the time coordinates of the matter will be completely unknown. From the above explanation, we can conclude that when the particle nature of matter is measured or displayed, the wave nature of matter is necessarily suppressed and vice versa. Wave function. According to the de Broglie's hypothesis, the relation between momentum and wavelength is found to be experimentally valid for both photons and particles. The quanta of matter or radiation can be represented in agreement with uncertainty principle by wave packets. Thus, it suggests that concentrated bunches of waves might be used to describe localized particles and quanta of radiation, the variations of which make up the matter wave is called wave function. Hence, we shall consider a wave function that depends on space x, y and z and time t and is denoted by psi of r, t. The wave function for a wave packet moving along positive x-axis is given by psi equals to psi naught multiplied with e to the power I multiplied with kx minus omega t. The quantity psi is assumed to have the following three basic properties. Number 1. It can interfere with itself so that it can account for diffraction experiments. Number 2. It is large in magnitude, whereas particle or photon is likely to be found and small elsewhere. Number 3. It will be regarded as describing the behavior of single particle or photon and not statistically distribution of number of quanta. Eigenvalues and eigenfunction. The Schrödinger wave equation is a second order differential equation. Thus, solving the Schrödinger wave equation to a particle system, we get many expressions for wave function psi. However, all wave functions are not acceptable. Only those wave functions which satisfy certain conditions are acceptable. Such wave functions are called eigenfunctions for the system. The energy values corresponding to the eigenfunctions are called eigenvalues. The wave functions are acceptable if they satisfy the following conditions. Psi must be finite everywhere, cannot be infinite. Psi must be single valued, which implies that solution is unique for a given position in space. Psi and its first derivatives with respect to its variables must be continuous everywhere. Thank you for watching this video. Please like it and share it with your friends and family.